you. So welcome to this morning problem session. Well, it's better to give in the morning, then you can talk a bit more. You still might have 10% of the time. Bruce asked me yesterday whether this is the new talk. He meant whether he will be bored during the following years listening to this instead of the previous 3 years. No, well, or maybe if we have more results, then we'll speak about this, or if we have results, because the idea of the talk actually came a week ago, or a bit more maybe, when we were asked by Christian Wegner to. Previously, we were also asked by Bruce and András, but they less than encouraged us to give talks. But then Christian Wegner wrote, and then I remembered that we had a nice discussion with Alantha, who is here, and Miklos Molnár, who gave a talk. It was after his talk a few months ago in Grenoble. And there, splitting off came up, and knowing András, I was sure that splitting off will be a ticket to speak here. So I thought, I have the ticket, why not use it? So that's it. And then we started to write emails, and some things we wanted became clearer. So the context became clear. So it's a problem session where you can place the problem maybe, or maybe I will just influence you in a bad way. I don't know. And there might be mistakes. Some people were happy also yesterday when we spoke. Oh, so if it's so recent, there might be mistakes. So you can watch, and indeed, there might be mistakes. Okay, so, oh, it doesn't work now. No, but it doesn't. Okay, after the talk, mistakes in the. No, but my computer is blocked, so no talk. So maybe. No, but it. Oh, okay, good. So, yeah. So if it's simple, let's make it complicated. Have you ever thought that an Eulerian trail is just a homomorphism of a circuit into the vertices of a graph? Yeah, some of you have thought about it. I didn't formulate it in this way, and I would maybe be mad if somebody would have thought in this way, Eulerian trails. But now we'll do that. So the context is that you have, you have a homomorphism, which is defined as usually of a graph to another graph, and every edge should have, the image of an edge should be an edge. So that's a homomorphism. And okay, and now a question, what are the, we already know that the homomorphic images of circuits are Eulerian trails. Now, what are the homomorphic images of paths? Then those who have thought about it, they will know. Okay, well, just so that you could imagine, here is an illustration. Here's a path. So what is the, or a degree to, I formulated here as a degree 2 connected subgraph. So here's a degree 2, a degree at most 2 connected subgraph. What are the homomorphic images of these? Well, I'll give you 5 seconds thought until giving an example. So here's the path, and you have the homomorphic image. So you have the numbers of the vertices, so the pre-image of the vertices on the right refer to the vertices of the path. So here's the homomorphic image, and of course, the answer of the question, as you all found, is that multigraphs with at most 2 odd degree vertices. That's the homomorphic images of paths. Okay, now the definition of the main heroes of the talk. The K-tree is degrees at most k, okay, just to speak shortly. And K-tree will be a homomorphic image of a K-tree onto a graph. Well, this object actually comes from the work of our co-worker, Miklos Molnár, but we call them bounded degree spanning hierarchies. And I never remembered all these 4 words, so I decided to introduce a new word for it. And when we write emails, we consequently, each of us uses his terms. Now, what if you put weight on the edges? We put weights on the edges of the graph in which you have the k-trace. I insist that the k-trail is a homomorphism onto, so not to a subset of vertices, but onto the set of vertices. The set of edges must not be onto, but onto the set of vertices. And you have the weights on your graph in which you have the k-trace, so in the image of the homomorphism. So it's better if that's a simple graph. So we'll suppose that's a simple graph. No loops, no parallel edges, because otherwise you wouldn't know. Yeah, the weights are in the target graph, but you will count the objective function in the source graph. You will count every edge with the weight of its image. So here is, for instance, there are 2 weights, 1 and 2, in the star. So the example, the star is the example. That's the source graph. So that's what you map to. No, that's a target graph. The star is the target graph. And you want to find a 3 trail in this target graph, which means that you define multiplicities and you map a tree onto it. And you want it to be as small weight as possible. So here is a 3 trail. Well, it has large vertices, so it is not a 3 trail in itself. A tree which has a K tree is a K trail, but this has a higher degree. This has degree 6. So it is not a 3 trail, but here is a 3 trail whose image, as the picture suggests, whose image is a 3 trail in that graph, because you multiply some edges and you can map this 3 tree to your graph then. Okay, now is it optimal, this 3 trail? It is not. Here is a 3 trail of weight 11. Right? Thick edges have weight 2, and thin ones 1. And you spare because you don't double one of the vertices that the other one doubled. Moreover, the other one was saturated, so it had degree 3 and 1 vertices. So only here there is a vertex which is not even saturated. So is the problem clear? No. Pardon?
You just mean the 3 dark edges.
I just mean, okay. So here is the graph G. It's a simple graph, right? We wanted 3 trays or K trays in simple graph. This is a simple graph, and it has edge weights 2 and 1. There could be many. Like, think about it. It's a generalization of, for instance, the Chinese postman problem, that you double some edges and then you want some trays. But here, instead of Eulerian trays, you want some kind of 3 trays, which actually they imagine as the way that Molnár presents it is that the salesman or the postman can split into. He doesn't have to go in one direction only, but he can split in several parts. So maybe it's better to imagine, not to imagine how you split salesmen, but that it's a group of salesmen, and then they go in different ways. Okay, so this is the graph in which you want a 3 trail. Okay, now this is the this is the three trait. Formally, the homomorphism, this is a free tree, right? It's a tree with all vertices at most 3, and it has a homomorphism to that graph. Right, so it has a homomorphism to that graph. And now the weight of the homomorphism you compute by the defined weights in your graph. So the edges which are mapped to weight 2 edges, they are counted twice. The edges which are mapped to weight 1 edges, they are counted once.
So the K tree, the pre-image, is basically anywhere, and you just drew it like
it's basically anywhere. You have to construct it. It's like your trail that modelizes. So the source graph, the graph that you map, is you construct it. It's somewhere. It's free. I mean, it's not free. It costs expensive 2 and 1, but you are free to do whatever you want. And then the weight will be defined when you map it, and you will count the weights in this way. Okay, then you could have, of course, like Mohit yesterday, that you put the weight, you put your graph into the weight function, and this is the complete graph. But I would like us to think in this way, that you have a graph, which is not the complete graph, and weights on it. And if you think in a different way, I will get confused anyway, but maybe you too. So to avoid confusion now, I still try. We look for K-trays in undirected simple graphs. The K-trays, they are spanning multigraphs. Spanning because it's onto the vertices that we map. And they use only edges of J with multiplicity 0, 1, etc. The weights are defined on J. For instance, if you map a path, then if we would not allow 0 weight multiplicities, it is a Chinese postman problem. So 2 trays are the Chinese postman. I will speak about that in more details. For k equal 2, it is if you want every multiplicity to be at least 1, that's the Chinese postman problem. But if you allow 0 multiplicities also, you want a subgraph which is has all degrees 2, and that's the spanning Eulerian tray problem, which is equivalent to the TSP. So and we allow 0 weight multiplicities. We go for the MP-Hart problem, and this is why we are interested in it. And actually, the approximation results, as you see, might have relations to. But again, I have a problem. No, it's okay. So questions. What kind of questions you can ask? And some of them our predecessors asked, of course. Well, given edge weights minimized, but now we remark that it's NP-hard, it contains the TSP. Now, the main problem I'm interested in is to give for 3 approximation for 3 traits, because the actual ratio is 3/2 for it. And so it's a problem for which now we know 3/2, and for which it seems that, and it seems a bit more accessible to prove 4/3, to have an experience how you go from 3/2 to 4/3. Now, but some basic questions arise. Now, I use different colors for different difficulties. So does there exist one for every k? K at least 2. When I mean every k, it's always at least 2. For every k in each graph, or when is a given multigraph a k-tray? Like 2 trays are exactly, we know, Eulerian trays or paths. But is it an easy problem? I don't know the exact answer, but we'll know something about this.
Sorry, isn't a k-tray also k plus 1 tray?
Yes, yes. So it's at most k. Yeah, so so that's it. So we know already, so we know the answer to the green. Yes, that's it. So the green ones are trivial. Right. But yes. But on the other hand, maybe the red ones are also, but I don't know. So that, I don't know the answer for the 2 thick red ones are the ones we'll focus on in the rest of the talk. But since we feel we seem to have fun, maybe, I don't know whether well, the chairman is very nice, so I think we. Pardon? Right. If k is big enough, so that's also another remark. If k is bigger than highest degree of your graph, then you will have one. But for small ones, of course, we want small ones typically. As I said, the main thing we want is k equals 3. Yes, because for k equal 2, it's MP complete, and yeah, but you can reduce, you can put artificially something, and you. So for any k, it's MP complete. There are some approximation results of our predecessors, and there are some remarks in the past week. So we will see that. I will go into that. Yes, and answers if the graph. So the problems are cut edges, right? Yeah, we will see that the problem is cut edges, and there is an easy answer if the graph is two edge connected. Maybe somebody sees that too. If two edge connected. No, to the previous question. So when is a graph a k trail? To this question, you have a nice answer, but almost an easy answer, an exercise level answer to when a graph, two edge connected graph. That was the ticket. That's where the splitting off appears, and I use my ticket, and it will be too late anyway after the talk to say that it was not the right thing. So now, sorry, it's a bit boring. I go back to two trays just to give the answer, but that we found already that every graph has a two tray, which you immediately have. Why? Because of the Chinese postman problem. That's the easiest way, maybe. We know that if you add a T-join to the edges of the graph, so you double the edges of a T-join, you have a postman trail. So you have an Eulerian trail, and that Eulerian trail is the homomorphic image of a cycle. So that's a two trail. So NP hard because we allow zero capacity, so I explained this already. But what is the approximation ratio for k equal 2? So another question, for k equal 2, well, we seem to know because it's sort of spanning Eulerian subgraph, but we know something about paths, some approximation ratios about paths, some approximation ratios about circuits, so about tours. What here we can have either of them. Does anyone know immediately? Did you think about what is the best approximation ratio for the best tour and path? If I would make a poll, there would be some people who say 3/2, some people 8/5 maybe, because you can do for all paths and you use the worst approximation ratio you can have. I could ask who would vote for 3/2, who would vote for 8/5, and I see that you are thinking. So yes, so who would say 3/2? Okay, so the rest 8/5. Or between the two, or between the two. Well, it is 3/2. You easily generalize Christofides algorithm. You just use the same argument, but there is a symmetric difference by two elements that you have to use, and you get 3/2. So yes, there is a 3/2 approximation algorithm for minimum weight two trails. Now, okay, so I just wanted to quickly repeat the way you get from Hamiltonian paths to spanning Eulerian subgraphs. In one direction, in one direction, you use the shortcut trick, so minimum weight, in order to reduce minimum weight Hamiltonian path, the usual way of stating TSP, to spanning Eulerian subgraphs. You determine the minimum weight spanning Eulerian subgraph, and you use the shortcut trick. You shortcut vertices that you have already visited once. To make the other reduction, so to reduce spanning Eulerian in 2G for arbitrary weights to Hamiltonian paths, you take the metric closure, you determine there the degree 2 optimum, and then you replace vertices, you replace edges, the new edges that you got and that were not in the original graph, by the shortest path between them. You don't change the parity, and in this way you get spanning Eulerian subgraph. Okay, and this trick occurs now for trees too, so that's why I wanted to repeat it. Okay, now a conjecture. The minimum, there exists a 2k-1 tray, at most as heavy as the smallest weight of a k tray, in the spirit of Michel's problem that was solved by Singh and Lau for k+1. Why it is 2k-1 here? Because that's what we need, so I didn't dare. That's the weakest that would be sufficient to prove some results, so that's what I dared to state. Moreover, the most interesting it is for k equal 3, and for k equal 3, twice k-1 is the same as k+1. So for we would like a 4 tray that is at most as heavy as a 3. K equal 3. K equal 3. Maybe. No, I mean for k at least 3. For k at least 3. For k equal 2, none of the other arguments work. We know already that that's equivalent. K equal 2 case is equivalent to the famous conjecture. So I mean, the conjectures I mean for k at least 3. And for k equal to 3, you have the 4 tray. You think that on the other hand, the k+1 case could be true for k equal 2 also. So a 3 trade, which is at most as much as the optimum for 4 trades. And Jens agrees very much because he gives the next talk and he would like to go forward maybe. So the approximation ratios are for this problem, those that were known, 1 + 1 over k-1, which gives only 2 for 2 trays, and 3/2 for 3 trays. Okay, and now from the conjectures you can prove 1 + 1 over k. That's just so it would be. It would give already, the formula gives the optimum for k equal to 2, but the proof is different actually. You have to separate the k equal 2 case. Indeed, the k equal 2 case you have to prove by using Christofides, and the other cases by just some induction. So also to prove the earlier results, it is a bit difficult to read the previous papers, so you can the only thing to remark is that you can choose a vertex so that only on one branch, in that vertex, you have vertices of degree plus bigger than k only on one branch, and all the others are already well done. There exists always such a vertex. It's easy to see, and then you can do easily induction. I won't go into details. I also just mentioned that you can't easily reduce this to k trees. K trees are really more general. There are simple examples which show that the optimum of a k trail is smaller than that of a k tree. it's a different thing. And so that's why also it's a relaxation of K-trees, and it could be a nice thing to study. Okay, so now three trays. So here is the three trays. I promised in the beginning also an easy remark, but maybe a ticket. A ticket to enter, not a ticket to... okay, so every two edge-connected, you are surprised seeing this first. Every two edge-connected graph is a three-trail. Every two edge-connected graph is a three-trail. It's just because you have a homomorphism in some sense is the reverse of a splitting off. So since you have splitting off of vertices of different degree than 3, you can split off, and then you have vertices of degree 3. This is a special case of Mader's splitting off, but actually special case of Lovaas splitting off just for two edge-connected graph. Suffices so you know it, and of course it can be proved more easily. However, I stated the splitting off because nobody stated the ticket, so I would like to compensate for all of you. So Lovaas is splitting off in a special form is here, and Mader's splitting off is here again. Maybe to come to this workshop already everybody knows these things, because at least you have read the book of András. There is a whole chapter about this. So it's not an advertisement, because I guess all of you have this book, but if by any chance you didn't, that's what I was expecting. If by any chance you don't, please, we won't ask until a month whether you bought the book. Okay, so I just recall, and just in time, I promised, and I keep it, the main problems that I don't know to answer. I actually think that characterize when something is a K-tray should be polynomially solvable. It's just the cut edges which play a role, right? The two edge connected are already three trays. So you have to double some single edges, and you have to take care of cut edges in a clever way. You seemingly can give necessary and sufficient conditions which are not so far from one another, and it could be polynomially solvable. Like for k equal 2, we have a trivial, well, an easy answer by Euler. Euler already answered. Two trays, and it wouldn't have any dramatic consequences to give a similar characterization for K-trays. But it resisted precise characterization, so I don't know the answer to this. And we are done. Thank you very much. Pardon?
You said that the minimum K-tray should be smaller than...
Yes. Well, 2k minus 1 is, well, for higher k...
but why did you say 2k minus 1? Why not k plus 1? Is k plus 1 wrong? Is that anything they suppose k plus 1?
No. I don't know. I just, you don't want to put a, to state a... You don't want to state a conjecture that somebody in the audience will say a counterexample. So I try to, I try to, that's what I said, I try to state the weakest one for at least k, at least 4, which is sufficient for the theorem. There was a theorem that if the conjecture is true, so that's what we need there. And that's what seems to be yes. Yeah, if it's false, then it's Bell's. If it's true, it's mine. No. Well, usually when you work a lot on a problem, you happen to know all kinds of things that you don't mention. But since time was a bit short, and if you looked at my abstract at the web page too early, then actually you see some differences. So they are not yet stabilized. Now they seem to, all those I spoke about seem to be quite stable, but we don't know, we don't know much more. So, no, I don't know. Great. But we'll be here with Neil in the following weeks. So.